All right. So how do you write an equation of a plane? Well, first of all, what does an equation of a plane look like in 3 dimensions? Ax plus by plus cz plus d equals 0. So notice that all x, y, and z have first powers. That's going to be a plane. Like in 2 dimensions, when you have ax plus by plus c equals 0 in 2 dimensions, that will be a line. But your general first degree equation like this in 3 dimensions is going to be a plane. 4 dimensions, and then it will be a hyperplane. Oh, and just, okay, never mind. Okay, so one of the first problems of tonight's homework is you have to sketch a plane. So I'll do something just like it, except different. 2x plus 3y plus 4z is equal to 12. So tonight's homework, the only difference is that there's a 6 right there. Okay? Now this is a plane. You guys gotta start getting used to drawing pictures now, yeah? This is the standard way. So the easiest way to graph a plane is plot the intercepts. Okay, so how do you get the x-intercept? Think about it. Any point that lies on the x-axis, like for example, the point 2, 0, 0, or 3, 0, 0, or 5, 0, 0, what can you say about the y and the z coordinates? They're 0. So to find the x-intercept of any graph in 3 dimensions, you simply substitute 0 for y and z. Like that. So therefore, what would the x-intercept be? 6. So the x-intercept will be 6, 0, 0. And likewise, what about the y-intercept? You plug in 0 for x and z, and you get 4. So the y-intercept will be 0, 4, 0. And then what would the z-intercept be? Plug in 0 for x and y. 3. Or you can give coordinates 0, 0, 3. Now, this is a plane now. Now, I don't expect, if I'm going to ask you to draw something, it will only be in the first octant where x, y, and z are all positive, because otherwise it gets very difficult to draw. You gotta have to be an artist, which I'm not. So I expect you to draw things in the first octant at least. So what you do is you connect these points with straight line segments like this. And then you can shade in like that. See? Of course, this is not the entire plane. This is the plane that's cutting into the first octant. Because a plane extends forever, yeah? Like that. But this is just the plane cutting into the first octant. You guys understand how this is going? There you go. That's how you graph a plane. And then, since today's lesson is going to be short, I'm going to show you how to graph other 3-dimensional figures in the first octant. Planes are easy because you can just connect the dots with lines, but then other graphs, they won't be lines. There'll be other curves, and it makes it a lot tougher. Okay, so how do you write an equation of a plane? Well, in 2 dimensions, how do you write an equation of a line? What are the things that you need to write an equation of a line? You need 2 things. Slope and a point, right? Oh boy, okay, let's go back to algebra 1. Suppose your teacher says, okay, I'm thinking of the line, the slope is 2/3 and it passes through the point 5,4. Can you write the equation of the line? Yeah, you just go y minus 4 equal 2/3 times x minus 5, right? That's the simplest way. So in 3 dimensions, now there's no such thing as slope in 3 dimensions. So what do you need? Well, these are the 2 things you need to write an equation of a plane. You need to have a vector that's perpendicular to the plane. So if you're going to write an equation of a plane, you need to find a vector perpendicular to it. Now tonight's homework is going to be easy because I'm going to kind of tell you what it is. But then in tomorrow night's homework, whenever it is, because there's no homework this weekend, yeah? You have to come up with that perpendicular vector. That's going to be the hard part. And why do I call a perpendicular vector n, physics people? Because N stands for
North.
normal.
North.
Oh, you said north?
Yeah. I know because it was pointing out.
Yeah, but then what if the plane is this way? What if it's pointing that way?
Yeah.
And come on, right? In physics, normal force. Doesn't normal mean perpendicular? Yes, in math and physics, normal means perpendicular. And then you need a point. Those are the two things you need to write an equation of a plane. So let me show you how it works. Suppose this normal vector is, give me some components. 2, 3, 4. And then you're given a point. 3, 2, 1. What would be the equation of the plane? It's really easy. It's actually easier than in 2 dimensions. Watch this. If this is the perpendicular vector, then the equation of the plane is 2x plus 3y plus 4z plus d equals 0. Where did I get the 2, 3, and 4 from? The perpendicular vector's components. How do I figure out this constant d here? What do you think I'm going to do? You're going to plug in the point. Exactly. So what happens if I plug in the point? Plug in 3, 2, and 1 here. What do you get? 6 plus 4 plus d equals 0. Therefore, d equals negative 16. Therefore, the equation of this plane is 2x plus 3y plus 4z minus 16 equals 0. Bam! That's how you write an equation of a plane. So you need a perpendicular vector and you need a point. So once you get this perpendicular vector, those are the coefficients of x, y, and z, and you just plug in the point to figure out the constant d. It's that simple. It really is that simple. So like I said, tonight's homework is going to be easy because most of the problems I tell you what the perpendicular vector is. But then the harder problems are you got to come up with that perpendicular vector. In fact, guys, I think we have one problem tonight. Here, I'll do a similar problem. Suppose you have a sphere. The center of the sphere is, give me a number, 2, 4, 3. Write the equation of the plane that is tangent to the sphere. I'm just going to draw a side view because it's hard to draw like the three-dimensional view like this. Plane tangent to the sphere. I guess that might do, but just draw it like this. Here's a plane. That's not a line now. So this is a sphere and a plane, not a line and a circle. And let's say that this plane is tangent to the sphere at the point. Give me some numbers. 1, -1. What number haven't we used? 5. Okay, write the equation of that plane. Well, what do we need to write an equation of a plane? We need a point. Do we know a point that's on this plane? Yes, 1, -1, 5. Do we know a perpendicular vector? Yeah, look at the picture. Come on, you got to know this on ACT and SAT. When you have a circle and you draw a tangent line, then when you draw the radius to the point of tangency, doesn't it make a right angle? Okay, so can you see a perpendicular vector to that plane? I see 2. You can either go this one or that one. Which one you want to do? It doesn't matter. As long as it's perpendicular. It doesn't matter how long it is or anything. It just has to be perpendicular. Shall we do this one then? Okay, now if you know the tail and the head, can we componentize this vector? Come on, this is tomorrow's quiz right here. Yes, head minus tail. If anybody goes tail minus head tomorrow, no free points on this quiz. It's head minus tail. So 2 minus 1. 4 minus -1. 3 minus 5. So that's this vector. Is that vector perpendicular to the plane? Yes. So therefore, what's the equation of the plane? 1x plus 5y minus 2z plus d equals 0. And how do I figure out what d is? You plug in the point. And please don't get confused between the point and the vector now. That's why you have different notations. Yeah? So if I plug in the point, you get 1 minus 5 minus 10 plus d equals 0. Therefore, d is equal to, come on, you guys can do the math in your head, I hope. 14. Therefore, the equation of this plane is x plus 5y minus 2z plus 14 equals 0. It's that simple. And anytime you work with planes in 3 dimensions, or it doesn't matter, in 4 or 5 and 6 dimensions, work with their perpendicular vectors. For example, 2x plus 3y plus 4z plus 5 equals 0. That's a plane. 2x plus 3y plus 4z plus 7 equals 0. That's another plane. What can you say about these two planes? They're parallel, they're perpendicular, or neither. Well, let's look at their perpendicular vectors. What's the perpendicular vector for this one? 2, 3, 4, right? What vector is perpendicular to this plane? 2, 3, 4. And what did we say yesterday? If one vector is a multiple of another one, then the two vectors are parallel, right? So think about it. If you have two parallel vectors, and then you have a plane perpendicular to it here and a plane perpendicular to it there, doesn't that mean the two planes are parallel? So in order for two planes to be parallel, their two perpendicular vectors have to be parallel, which means one vector has to be a multiple of the other one. Okay, that's kind of obvious, right? Pretty easy. How do you tell if two vectors are perpendicular though? Come on, this was last night's homework. The dot product is equal to 0. That's guaranteed going to be on the quiz, okay? The dot product is 0. Okay, so which means, how can you tell if two planes are perpendicular? That means their perpendicular vectors have to be perpendicular. Okay, so here's a plane, 2x plus, let's just use that one again. 2x plus 3y plus 4z plus 5 equals 0. And here's another plane, 5x plus 2y minus 4z plus 17 is equal to 0. First of all, are these two planes parallel? No, you can kind of just see it. What's the perpendicular vector for this one? 2, 3, 4. What's the perpendicular vector for this plane? 5, 2, negative 4. Are they parallel? No, because one is not a multiple of the other. But they could be perpendicular. How do you test that? If the dot product is 0. Okay, how do you compute the dot product of two vectors? Multiply the x components, multiply the y components, multiply the z components, and add them up. What do you get? 0. So this vector is perpendicular to this vector, which means this plane is perpendicular to that plane then, right? Because think about it. Okay, look. If two vectors are perpendicular, like this, then the plane would be here, right, perpendicular to this, and the other plane would be perpendicular to that. So therefore, doesn't that have to be a right angle? So the key is, anytime you have to work with planes, work with their perpendicular vectors. Like one problem on tonight's homework is find the angle formed by two planes. In fact, let's do a problem. So think about it. You have two planes intersecting like this. These are planes now. How do you find this angle right there? Look at their perpendicular vectors, okay? So here's a perpendicular vector for that one. Here's a perpendicular vector for that one. Why is it that this angle here is equal to that angle there? Geometry, right? Look, what can you say? Okay, how many degrees are there in a quadrilateral? 360. But this is 90 and this is 90, so therefore these two angles have to add up to 180. So if this is theta, wouldn't this angle here be 180 minus theta. Right, so therefore this angle here is theta. The angle between the two vectors is the same as the angle between the two planes. So again, anytime you're working with planes, work with their perpendicular vectors. So example, let's just use the same darn thing. 2x plus 3y plus 4z plus 5 equals 0. And give me another one. How about the 5x minus 2y minus 3z plus 1 equals 0? What is the angle between these two planes? Well, it will be the angle between their perpendicular vectors. So what vector is perpendicular to this? 2, 3, 4. What vector is perpendicular to this plane? 5, negative 2, negative 3. Now, if you have two vectors, put them tail to tail, can you figure out what their angle is? Yes, that's last night's homework. That's going to be on tomorrow's quiz. And how do you do it? Remember, I told you, anytime it says compute an angle, what are you going to do? The dot product thingy. Have we forgotten? How can I forget when I never learned it? That's why you got to do homework. Cosine theta is equal to the dot product of two vectors divided by the length of the first one and then the length of the second one. Guarantee you can use this at least once tomorrow. Okay, so here are the two vectors. If I want to find the angle between them, what do? You dot product them. Okay, how do you find the dot product again? Multiply the x components, multiply the y components, multiply the z components, and add them up. That's how you compute the dot product. It's that simple. Then you got to divide it by the length of this one and the length of this one. Okay, you guys better be good. I'm going to call on people here. What is the length of this vector? Wang, Kai. Wait till I get to the downbeat. No, you're late.
I already forgot. Wait, let's go around time.
No, wait till. Did you watch, what movie am I thinking of? The guy conducted the jazz band and he was really mean. Whiplash. Did you guys see the movie Whiplash? Okay, you guys need to see that. No, you're late. Here's, the downbeat is here. Yeah, there you go. 129. And the other way, what is the length of this vector? Wait, I'll give you time to think. Wait a minute.
Square root of 38.
Yeah, there you go. See, you guys can do it. So that comes out to -8 over, oh boy. Who picked these numbers? 38 times 29. Who's got this one? Kusamoro? Okay, well, if I were multiplying 38 times 29, I would think of 29 as 30 minus 1. And then distribute. Okay. Just do it the old-fashioned way. 2 carry 7, 6 carry 1. Did I do that correctly? It must be correct because I'm the teacher, right? There you go. So therefore, what is the angle between the two planes? Okay, wait, Kusamoro.
Cosine inverse of -8
Okay, there you go. See, you guys got it. And of course, that negative means the angle is obtuse. It's bigger than 90 degrees. Of course, if I'm going to write a problem for a quiz or test, I'm not going to make it come out ugly. I'm going to make it come out nice. Like, I'll make it come out to like -√3 over 2 or something. So then you know it's a, what would that be? What would that be if it were -√3 over 2? 5 pi over 6 or 150 degrees. That's just horrid. Okay, what else do you got to do? Tonight's home, this is the easiest homework of the whole chapter, I think. Oh, number 11. So we already talked about this already. So in 2 dimensions, what is this formula for? In 2 dimensions, what does this formula do? The distance between a point and a line in 2 dimensions in the Cartesian plane. But if you tack on another dimension like this will be the distance between what? A point and a plane. And that's what we're doing tonight. We're doing planes. Okay, so suppose you, let me give you a plane. Okay, let me think. If I want to make the answer come out decent. 2x minus 3y minus 6z equals, give me a number. Let's see if you're good, if you guys are good. Give me a number.
1.
1. And then give me a point.
2.
2, 3, 4. How creative. Okay, what is the distance between this plane and this point? All you gotta do is use this formula. Okay, but we gotta do one thing first. The equation has to be in general form. That means you gotta make one side 0. So what you gotta do is you gotta bring the 1 over. So minus 1 equals 0. Let's see if you guys, I gave you an opportunity to make the answer come out nice. Let's see if you actually did it. So this is A, B, C, and D. That's x1, y1, z1. Plug and chug, baby. Absolute value. 2 times 2 minus 3 times 3 minus 6 times 4 minus 1 all over the square root of 2 squared plus negative 3 squared plus negative 6 squared. Okay, what is the numerator going to be? Cruz. Okay, I'll give you time to think. Oh, it might come out nice.
Negative 30.
Yeah, but there's absolute values here.
30.
Okay, 30. Come on, distance cannot be negative. Okay, denominator. Who's got the denominator here? Again now.
Root 30.
Wait. Just think a minute. There's a very famous scene in Whiplash you gotta see. No, you're behind the beat. No, you gotta watch that movie. That movie is really good. If you like jazz band and music, that movie is really good. Okay, again. There you go, 7. See, if you guys were good, you should have made that thing come out to 28.
Plus 1.
Oh, so just put plus 1 instead of minus 1. Would that have done it? Yeah, but you guys did it. So now we're stuck with this ugly answer. So if I were making the problem, I would make the numerator divisible by 7, because then you get a nice answer, yeah? That's what I do when I write quizzes and tests. Anyway, but come on. This is a very simple formula. Okay, now, since we have time, who's 10th grade here? No 10th graders in this class. Okay, then, well, you might be taking multivariable calculus when you go to college. Well, if you go to college, right? So here. So what happens when we get to multivariable calculus? Like what we did is we studied conic sections last chapter, remember that? So you have parabolas, ellipses, hyperbolas. So what would be their 3-dimensional counterparts? So instead of a parabola, you have a paraboloid. Here. I had the Fab Lab make me one. This is a paraboloid. 3-dimensional parabola. And then it has a focus, and then of course you aim it toward the heavens, and then everything goes toward the focus, right? What is the 3-dimensional counterpart of the ellipse? An ellipsoid. What about hyperbola?
Hyperboloid.
Hyperboloid. Except there's 2 kinds of paraboloids. I'll talk about that later. Let's sketch an ellipsoid. So what would an ellipsoid look like? The equation? Well, it looks just like an ellipse, except it has a tacked on third dimension. X squared over, give me some numbers here. 16 plus y squared over 9 plus z squared over 4 equal 1. See, like that's an ellipse, right? But then you tack on a third dimension, now it's an ellipsoid. So how would you sketch this? What if I told you sketch this in the first octant? So now it's not enough to just look at intercepts. Okay, well let's do the intercepts. What would the x-intercept be? Substitute 0 for y and z. And then you got x squared over 16 is equal to 1, which means x squared equals 16. So x equals plus or minus 4. So you're going to have 1 on this side, so this is 4, 0, 0. But then you would have on the other side. So if you were to graph like the entire thing, then you got to go like dotted lines in the back going to the, but that's so complicated. That's why if I'm going to ask you to graph something, I'm only going to ask you in the first octant only because it's too complicated. Even artists might have a hard time. What are the y-intercepts? Plus or minus 3. But we're not going to go backwards over there. We're just going to take the positive one. 0, 3, 0. What are the z-intercepts? Plus or minus 2. So here's the positive one. And then, of course, you would have one down there, but we're not going there. And now, do I just connect it with straight lines? No, because that would be a plane. We're not graphing a plane anymore. So instead of just the intercepts, now we're going to look at something called traces. So there's an xy trace. There's an xz trace. And then there's a yz trace. So basically, the xy plane is right here. If you think of this as the corner of a room, the xy plane is the floor, right here, that's the floor. This wall right here is the xz plane. And then this wall over here is the yz plane. So where does, whatever graph you're thinking about, where does this graph intersect these three planes? That's what we call traces. So the xy trace is right here. Where does the ellipsoid intersect the floor right here? Well, think about it. What's the equation of this floor? Or what can you say about the z-coordinate if you're on the floor right here? It's 0. So what you would do is substitute 0 for z. In fact, the equation of the xy plane is z equals 0. That's because every point in the xy plane, the z-coordinate is 0. Okay, so what you do is, all you're going to do is substitute 0 for z. What do you get? You get x squared over 16, that's an ugly square, plus y squared over 9 equal 1. Hey, I know that graph. Do you know it? You're supposed to respond.
Me too.
What? What did he say?
Me too.
You too.
Yeah.
No, we know this graph.
Oh, look.
Ellipse, thank you.
Oh.
We just started. Okay, so in the xy plane, like if I ask you to graph this ellipse, what did you go? Oh, you go 4 to the right, 4 to the left, 3 to the up, 3 to the down. Looks like that, right? Okay, but see, here's the xy plane. It's like at an angle. And we're only graphing it in the first octant. So how would you graph that ellipse? But we're only going to graph this part of it, right? When both x and y are positive. How do I draw that, like right here? Something like that, right? Because you're looking at it at an angle. Okay, what about the xz trace? This wall right here, the xz plane. Well, what can you say about the y coordinate in the xz plane? In fact, that's the equation of the xz plane. It's y equals 0. So what you do is you substitute 0 for y. So if you substitute 0 for y, you get x squared over 16 plus z squared over 4 equal 1. That's one ellipse in the xz plane. So like if you had x and z axis, then you go 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 1, 2. So in this plane, that's the ellipse, but we're only going to be drawing this part of it right there. Wouldn't that be this right here? See, now you got to think three-dimensionally. And finally, what do you think for the YZ plane? This wall right here. You plug in 0 for x because the equation of the XZ plane is x equals 0 because every point has an x coordinate of a 0 in it. So if I plug in 0 for x, what do you get? You get y squared over 9 plus z squared over 4 equal 1. Hey, that's one ellipse. So if you were drawing it in the YZ plane like this, then what? You would go 1, 2, 3, 1, 2, 3, 1, 2, 1, 2. But we're only going to graph that part of it, which is right there. And then you use your artistic skills. I don't have much, but kind of just shade it in like that. So what fraction of the ellipsoid is this? 1/8 of the ellipsoid. That's right. That's what it is. Here's an interesting thing. What is the area of a circle? Pi r squared, right? So if you have an ellipse like this, you remember I got the major axis, minor axis. What do you think the volume of an ellipse is? It's pi AB. Now, why am I saying volume? What is the area of an ellipse? Pi AB. Because in a circle, it's just that these two things are equal, right? Pi r, pi r squared. It's like the same thing. Okay, so let's see if you can catch on. What is the volume of a sphere? 4/3 pi r cubed. What do you think the volume of an ellipsoid is? If you think of this as a squared, b squared, and c squared, what would be the volume of an ellipsoid? 4/3 pi a, b, c. That's right. It's just that in a sphere, all three of these are all equal. I don't like thinking of things like that. And like I told you, we're running out of time already, but there's two types of hyperboloids. Like an ellipsoid and a paraboloid, it's easy to think about it, right? Like, what if you have a parabola and you revolve it about its axis of symmetry? Wow, you get a paraboloid. But with a hyperbola, think about it. Let's say a left-right hyperbola. What if you revolve it about the x-axis, like this? What are you going to get? We get these two cups like this, yeah? We call this a hyperboloid of two sheets. I better write that down. Hyperboloid of two sheets. That's because in order to graph it or make it, you got to have two sheets of paper. Two sheets. But what if I told you take the same hyperbola and revolve it about the y-axis like this? Then it would look like that. We call this a hyperboloid of one sheet because you can make that one sheet of paper. And when you go to 3 dimensions, we got all kinds of crazy things. We got this thing called the hyperbolic paraboloid. Did you guys ever notice that? It's on the wall right there, man. The hyperbolic paraboloid. Wait, I'm gonna. Hyperbolic, zoom in. This is for the people on the video, they're right there. Hyperbolic, you know what's neat about the hyperbolic paraboloid? Look at this point right here. Look at this point, right there. Is that a maximum point or a minimum point? Like if you have a paraboloid like this, wouldn't that point up there be a maximum point? But if the paraboloid was this way, then wouldn't that be a minimum point? Okay, so look at that point right there. Is that a maximum point or a minimum point? It's both, exactly. Because if you look at it this way, that's a minimum point. But if you look at it this way, it's a maximum point. That's crazy. How can a point be both a maximum and a minimum? Well, it is. You know what we call that in mathematics? A mini-max. That's what it's called, a mini-max, or some people call it a saddle point, because it looks like a saddle. But that's the kind of crazy stuff you have when you get to 3 dimensions. And just imagine 4 dimensions. All right, we are done.